Okay, I think it's time. It's 11:10. I hope you all got new coffee. At least I have. So I would like to invite Xavier. Yeah, he's there.
Yeah.
So this will be a different talk about concrete in practice, how you can use it in real projects to build with it. And Xavier is, of course, an expert on that since he is working at one of the biggest contractors in Belgium, and also they work all over the world. So, Xavier, the floor is yours, and let us see how that works in practice.
Do you see my screen?
Yeah,
My
we can see.
PowerPoint, yes. Uh, Let me put it in presentation then. It doesn't look like it works as a presentation. Now it's
Now it
okay.
works. Yeah.
Now it works. Excellent. Okay. Well, thank you first. I'm really happy to be here, even if I would have preferred to be to meet you in real life. Um, my name is Xavier Farina. I'm the concrete technologist for Besix. Now it's been 11 years that I'm working for Besix, and 10 years about regarding concrete technology. So everything related to problems of concrete or special concrete in the company. So what I'm going to talk about is, first I will do a small introduction about the company. I will then try to show some examples on why do we need to go a little bit more into detail into the practice of the mixed design, what happened on site, what can be the consequences of the choices that we are going to do. Also, then, when how can we do a project analysis, or what are the needs of the concrete that we want to see exactly how are we going to choose the materials. We will do a small quiz, just a few questions that we will try to answer together, and if we can, we will also have a look at other principles that are a little bit related to the mixed design, but at least it will be some principles that we can use if we don't have the choice on the mixed design. Please feel free to interrupt me as soon as you want to. If you have any question, it's always better to have also some kind of a live show, even if it is through the screen. Quick introduction about Besix. So as Eric said, yeah, we are the first contractor in Belgium. We are present in 25 countries with a little bit more than 12,000 people. Here you can see some of the projects that we have done or that we are working on. These are projects in Belgium. Maybe you can recognize the Atomium. It's like our Eiffel Tower in Belgium. We are really proud to have done the renovation of it. And some other projects more around the world. Here you can, I don't know if you see my pointer, but you can see the Burj Khalifa, which I guess is the most known building that we have done, at the highest tower in the world. We are quite busy also into stadiums, but maritime infrastructure also, quite a little bit of everything. And that's why the concrete is always different for that. You can see that where we are present a big part in Belgium, but also now in Australia. The Middle East is one of the biggest part of our work also, and then we still have other projects in other countries, also in Africa. Very interesting project there also, and the biggest activity is buildings. We have also an engineering department, which is quite interesting because this is where we have we are working on innovations and new technologies, and that's also one of the reasons why we are part of Spartings. We are really interested in that. We are using a lot the BIM modeling, and we have a department with soil mechanics and concrete technology. this is also the reason of my presence. And we have a lot of draftsmen and technicians that are working with us together. Now that I have done the small publicity part, let's talk about concrete now. So I really like to show some example, but especially what went wrong, to show what are the why we really need to go into the practice of the mixed design. First example is this is a picture of a tower in Baku in Azerbaijan. And when you see the picture, it's always nice to see, oh my God, it's a nice tower. The picture is nice. We see that it's going really well. And this is what we like to show to the people also, to show that we are working on a really nice project. But if you look a little bit deeper, a little bit closer, you can see things like this. Of course, it's not a big deal in this case. And it's not directly related to the mixed design itself. Here, it was more a leakage in the formwork. But anyway, this is a problem that we don't talk about when we show the nice pictures. So, but it's important to see that you can have this kind of problems, this kind of honeycombs, because you have a leakage in the formwork, and this can lead to problems of corrosion because the water can go inside the concrete and reach the rebar, and then the corrosion can start. This is typically things that we want to avoid. In this case, it was also not a big deal because it was an internal wall, so it's not like it was a swimming pool. We don't have any water inside, so it's not a big deal. But anyway, we want to avoid that. It's our responsibility to the client also to deliver something quite good. A second example is a jetty. This is a jetty in Mozambique. And the idea was, this jetty has been built 50 years ago, by the Portuguese at this time. The idea was to see if it was possible to refurbish the jetty, to use it again, to have boats coming there. So we went there to see if it was possible or not. And first, when you see this picture, it looks quite nice because it's in a nice country. But again, if you look a little bit closer, you will see things like this. You will think might be a problem to refurbish this. Maybe it looks like there's a lot of damage. But anyway, this is still a possibility. You can cast new concrete, you can clean the rebar, replace the rebar if it's necessary or not. But this is where it was really interesting, and especially in terms of mixed design, is that we have taken some samples of the concrete, we brought them to a lab, and then we have done an analysis to see what was the mixed design of this concrete, what was the materials that have been chosen for this concrete. And then we have discovered that the concrete has been made with seawater. Problem of seawater is that there's a lot of chloride inside, and so the chlorides are going to attack the reinforcement. So at the end, yeah, it was not a really good idea to continue refurbishing this structure. So that's why, of course, mixed design in this case is really important because, don't use seawater in the concrete, especially if you have reinforced concrete. This is another example of a bridge that we have done in Equatorial Guinea. In this case, it was not to show what went wrong because at the end everything went well. But when we are in the middle of the jungle like this, bridges can be really far from the cities. And the big challenge in this case is to bring the right materials that we need to do the concrete, especially for bridges like this. You might have some high strength concrete. The weather is not that good also. We can have a lot of rain in one go. So it's, on a logistic point of view, it is really complicated to work in some region of the world, especially when you're really far from everything. Another example to show really the importance of the choice of the concrete, and to show that concrete is not just something that is gray and that you cast on site. This is a project in Saudi Arabia. it is a stadium, a really big stadium, and it was the client. Well, we were supposed to do this stadium in 3 years, and after 1 year of after starting the works, the client said, "Okay, I want you to finish the stadium in 1 year because I want to have a football game in the stadium. So you have to finish 1 year earlier than scheduled." Of course, we said yes because we like the challenge. Well, okay, now when you say yes, then after that you have to do it. So that was a big challenge because these beams, the 70-ton beams that we were precasting, I will show you in the next picture. You can see that these beams are the beams that we are putting here, and then you have other beams that are coming here, and then you will have all the seats on these beams. So these beams, we were precasting them in the center of the stadium. And the idea, because of this acceleration, was to be able to cast the beams anytime during the day. And the morning after, we were supposed to remove the formwork and lift the beams without doing any problems. So we did a lot of modification on the mix design. We worked a lot on the different super plasticizer that we were going to use to reduce the water cement ratio, to increase the strength, and because of that, we were able to lift the beams quite fast. Other example why we need to take care, but well, it's the cracks. But I think it's also the reason why everybody's here, is to avoid this in not only on working on the mix design, but also in the self-healing part of the concrete. This is one of the most interesting example, I think, of the choice of the mix design. This is the first concrete of a project in Belgium. It was a lock. We were doing a really huge lock. The quantity of concrete, it was 220,000 cubic meter of concrete in total for the whole project, and this was the first concrete. The specificity of this project is that we have decided as we were going to dig a lot of quantity because it was a lock, we decided to take back all the gravels and the sand that we were able to find in the ground and reuse them into the concrete. It's a good idea. We can save a lot of money, a lot of carbon footprint with this because we were reusing exactly what we were using. But the big problem is that, well, you have to deal with your concrete. You don't have the choice. It's not like you go on the market and say, I would prefer to have this size of aggregate or this size of aggregate. No, you have to deal with what you find into the ground, and you try to, like Peter explained, you have to make your curves to try to find a good concrete. Unfortunately, when you see this, you don't need to be an expert to see that this is not a good concrete. We had a lot of segregation, and one of the reasons was that the curve was not perfectly adapted, and we had a lot of crushed sand. So this is really a good example to show that you don't just put some material together to have your concrete. You really need to analyze them to do all the steps that Peter shown just before. One of the last example is, I don't know if you know this project, it's not built yet. This is supposed to be the new highest tower in the world. This is in Dubai. It's the Dubai Creek Tower by the architect Calatrava. It's going to be more than 1 kilometer high. And this is a really, really big challenge in terms of concrete technology and mixed design, because first, the compressive strength is quite high. The concrete for all the tower is going to be a C100, 115, so way more than the C30, 37 that we are used to work with. So this is going to be a high-strength concrete that needs to be pumped at more than 800 meters in one go. So this is also something that we need to work on the mix design. And but I will show you a few examples also on how can we deal with the pumpability of the concrete by choosing the right material. Another problem or challenge, let's say, is that this concrete has to be pumped, but after that it will be put in walls. It will be cast in walls of more than 3 meter thick. The problem is that it's going to generate a lot of heat, and as we have a lot of cement, because it's a high strength concrete, it is going to generate a lot of heat. So we have also to deal with that. Well, for the moment, it's just testing about this this project. It's not built yet, but anyway, the mix design is there, and it was a lot of work, of course, to be able to produce this. Last example is really to show that, yeah, practice is really necessary. It's not just because you know that concrete is going to be hard that you know it. When you see this guy, maybe it would have been better if he had a look at what can happen with the concrete to avoid this situation. I think he was avoiding the traffic jam, and then he saw, yeah, okay, maybe it would be interesting to follow a little bit more about the concrete in practice. So now that we have seen a little bit more about what can go wrong and why we need to go a little bit deeper in this situation, what happened when we go on the project for the first time? We need to see what are the real needs of the concrete. It's a little bit about what I have explained just before. The first thing that we need to check is what are the concrete enemies. There's a list of situation. Oh, sorry. I thought it was appearing everything. Okay, so these are the exposure class. It's about the durability of the concrete. We need first to know, okay, where the concrete is going to be cast. Is it going to be inside a building where nothing can happen? Or is it going to be concrete for a swimming pool? Is it going to be concrete that will be in contact with seawater, with a lot of chlorides, for example? All these kind of things we need to know before starting the concrete. So the exposure class with X, so this is as per the European standard. Like Peter said, in Belgium we have also the environmental class, so EG class, but I'm going just to talk quickly about the exposure class as it is more general because it is used a lot in Europe and now more and more in the world also. So we need to know first, if you don't have any risk, then it is going to be X0. We need after that to know what can happen to the concrete or the rebar. In this case, what you are seeing right now, it is what can happen to the rebar. The rebar, we have three main problems. That is the carbonation, which is the reaction with the CO2 of the air. And it's going to be the reaction with the concrete, but because of this phenomenon, you can have corrosion of the rebar. So this is something that you need to know. Then you have everything related to the corrosion induced by the chlorides, but other than from the seawater. So for example, de-icing salt, this is something that we have a lot in Europe, but also from the chloride from the swimming pools and things like this. And then XS, which is related to the corrosion induced by the chlorides from seawater. This is really important as soon as you are doing concrete for marine structure. The XS is very important, especially that the chlorides are making a lot of troubles. On the other side, you have also the concrete attack. So this can happen even for non-reinforced concrete. And then you have the XF related to everything related to the freezing, with or without de-icing agents. So of course, this is mostly important for countries where you can have freezing. And then you have the chemical attack. Chemical attack, you have different cases. in practice, I mean, I'm talking about Besix at least for our project. The biggest problem is the sulfates that we can have in a lot of different places. We can have this in seawater, but we have this also in the ground, for example. And we are building quite a lot of sewage treatment plants. And when you have sewage treatment plant, you have almost everything. You have the chlorides coming from the process, but you have also a lot of sulfates. So in this case, for example, this is where the concrete is really important because it can be attacked quite a lot by different process. When you have all these exposure class, like Peter said, you have some requirement about concrete, about the water cement ratio, the minimum strength class, and the minimum cement content. So based on this is really the basis of your mix design that you're going to do. You need to know where I am going to do my concrete. You're not going to cast a concrete with only 250 kgs of cement in a marine structure because you will have troubles with the chlorides directly. This is a good example just to illustrate a little bit more the exposure class. You can see that you can have really a lot of different classes in on the different elements, depending on if it is horizontal, vertical, because you will have projection or not, and you will have each time a number just behind the exposure class that will be then related to the table that we have shown before. So you can see that it goes from internal elements where it's X0, and then when you're in the seawater, this is the worst case, when you can have carbonation, you can have attack by the chloride from the seawater, but also chemical attack and also freezing if it is in a freezing country. So this is to show what is the most important thing about the first thing that you have to take into account is where am I going to put this this concrete. Then a second thing is the workability of the fresh concrete. Of course, it's not going to be the same if you have a fluid concrete or a concrete that is I wouldn't say hard, but almost hard. You can see the difference with the slump test. I don't know if you are all aware about the slump test, but I think that at least you will see it this afternoon in the virtual lab. So basically is you have what we call the Abram cone, which is a cone that is 300 millimeter high. You can see it in dashes here. You fill it within concrete. It is a standard method. And then you remove the cone and you see how much the concrete cone is collapsing. And you have this S1, S2, S3, S4, and even S5, which is how workable is the concrete, how fluid is the concrete. To show you some two extremes, in the first picture on the left, you can see really, we call this a dry concrete because it's usually a concrete with not so much water, but now it's more with the less admixture. So this is really, this can be interesting for concrete where, for example, for slip forms, horizontal slip forms. You can use this for stairs, for example, to avoid that the concrete is going everywhere. But most of the time in big projects, you need to have a more flowable concrete, such as the one on the right picture. We can think that this might be a self-compacting concrete. I don't know if you have heard about already the self-compacting concrete, but no, in this case, it's just a high flowable concrete. So you can see that it's exactly the same test, but it will spread a lot more. The thing on this picture, we are not measuring the slump anymore. We are measuring the flow, which is the diameter of the spreading of the concrete. We need to be careful, and this is really related to the mix design also. We need to be careful a lot on the quantity of water that we're gonna use. If you are using too much water, you will have something that will not be homogeneous at all. And you will see that you will have some segregation, which is really the aggregates that are going to be on one part and the cement paste really fluid on the other one. Concrete needs to be really homogeneous. I had the case one when a concrete supplier told me, yeah, I can make you a self-compacting concrete. And what he did, he just took the basic mix design, the one that we were using on the project, and he added a huge quantity of water. So of course it was so fluid, but at the end it was just a gray soup with a few gravels somewhere. So it was, of course, absolutely not a good concrete. We really need to take into account and to follow all the steps to have something really homogeneous. One of the next parameter that we need to know is, are we going to pump the concrete? Because now more and more we are using pumps, because pumps, it's quite easy to use. We have pumps like this on the truck. It's really easier to be able to pump the concrete from one side to another one, or also for towers. That now that we're making towers higher and higher and higher, we will have more pumps that are going to go really high, or longer pumps. And this is really important, because if you are using the wrong concrete into a pump, you will break your pump because the friction will be too high. And trust me, we have broken already a few pumps, and this is not something that you want to happen. So this is why it's really important to choose correctly the concrete, depending on the if it is pumpable or not. So in this case, you can see the mobile pump. So it's you can see the truck on the side, where the concrete mixers are coming and just putting the concrete inside a pump, and it will go through all the pipes to go exactly at the place where you want. But when you pump, it's also talking about vertical pumping into high-rise building. This is the example of the Burj Khalifa, where we needed to go. So you can see that it was more than 600 meters, the final pumping, and it's really a question of logistics. We had the three different pumps. All the pipes here are going inside the building, and then horizontally, and then vertically. Here, the mix design is really important. You cannot have too big aggregates. You need to have a really fluid concrete, and you cannot have any type of segregation. As soon as you have a little bit of segregation, so the separation of the aggregates and the cement paste, you might have a blockage into the pipes. And if you have a blockage into the pipes, it will the pressure will go too high, and then your pipes can really explode. Now, just want to break a myth, because I still hear a lot of people saying that the concrete, when it's hard, it's because it is drying. So it's like glue. The glue usually is because it's drying. The concrete, people say, yeah, concrete is drying, now it's hard. Absolutely not. It's not the case. It is because actually it needs water. It is a chemical process. It becomes hard because this is what we call the cement hydration. And this is just quite a small example. And so the cement hydration is the contact in contact with the water. The cement grains are going to have this reaction. I will not go too deep into the reaction, but what is important here to know is that this reaction is exothermic. It will produce heat during the hydration. So at the moment where in the middle of the reaction, it will generate a lot of heat. But the problem is that if you have massive concrete, and this is where I want to go, if you have massive concrete, this heat will not be able to go out of the concrete smoother. So that's another example. This is a raft of 20 meters thick. It's the raft of the new tower that I was talking about at the beginning. So the first 16 meters are in C70, and the last 4 meter or in C100, C100, 115. As we have a lot of cement inside this concrete, it will generate a lot of heat. And the problem with this heat is that it's going to stay inside the concrete and will go out of the concrete really slow. This can lead to cracks because of thermal difference of inside the concrete. And we can also have another problem that is called delayed intragite formation, which can give a lot of troubles in a few years, actually. So it's something that we need really to know before. I will show you an example of mass concrete and the calculation of the temperature inside the concrete and why it is really important to avoid problems. But it is really important to know it as soon as possible if we are going to have this kind of massive concrete. This can start with elements of around 1 meter of thickness. You can already have a lot of troubles just with 1 meter thick elements, and this needs to be taken into account into the choice of the materials. And one of the last most important thing actually is the compressive strength. You have seen during the presentation of Peter that you need to calculate the compressive strength. And of course, this is actually one of the most important thing that you need to know, because you need to know exactly what is the compressive strength that you're going to use. This is coming from the client, or at least from the design office, and this is why we are talking about concrete like C3037. So it's the strength on the cylinder samples and the strength on the cube samples. We are doing this by crushing these specimens. When it explodes like this, usually it's a high strength concrete and it's quite impressive. But it's really important to know because it will have an impact on everything, on the workability of your concrete, on the heat that is going to go out of the concrete, and on all the parameters that I have talked about, also the durability. So this is really important to know, is what is the compressive strength. And of course, and this is the last one, is what is available. As soon as you work somewhere, it can be anywhere in the world, you will not be able to bring the materials that you are used to work with from one on another country. Remember the picture I was showing you in the middle of the jungle? You cannot say, okay, no worries. I know that I have a really good sand in Belgium. I will bring it to the project. This is not possible, of course. So you need to see, okay, what can I see locally? Like the example of the lock that I was showing. More local than this you cannot do, is taking directly the aggregates from the ground. This is one really good solution, but you need to take this into account. When you are in the middle of the jungle, there are not a lot of different quarries or possibilities to find the aggregate. There are not so many cement available. And again, you're not going to bring all the time cement from another country. It's not that easy. So it's really try to work with what you have on site or locally at least. Do you have any question before going into how we can choose this material? Feel free to raise your hand and ask. Otherwise, we can keep it for the end. No one? Okay, let's have a look at the choice of the material. Well, we have seen concrete is cement, aggregates, water. When we talk about aggregates, we're talking about gravels and sand. We have also plasticizer. This is something that you are going to have a look at it this afternoon, I think. These are the simple material of concrete. But let's have a look first at the cement. So basically, we are using this kind of cementitious material. The first one is OPC. This is the ordinary Portland cement. This is the what we call in Europe the CEM1. This is just like pure clinker almost. This is the most common cement, and this is what you have to use. Then we have the GGBS. This is the ground granulated blast furnace slag. So it's a byproduct from the iron production, and this is something that we can use as an addition, but this is also what we can find in what we call the CEM3, for example. I will just show you in the next slide a table with all the denomination of the cement in Europe. But GGBS, what is important to know is we use it a lot to reduce the heat of hydration of the cement. So when we know that we are going to have massive concrete that is going to generate a lot of heat, we are going to use cement with GGBS. It will reduce a lot, really a lot, the heat of hydration, and we are using it around 60-65% of replacement of the cement. GGBS is also really good for the durability, which is resistance to chloride, resistance to sulfate. As soon as we want to have a durable concrete, because it will be used in an environment where you can have some attack mechanisms, GGBS will help a lot. So that's why actually we are almost using all the time GGBS in our cement, because we usually need to reduce the heat of hydration because, well, we have quite big elements, so we want to try to reduce the heat of hydration, but we also need to have something that is going to resist during the years to the different attacks that we can have. The problem is that on the workability, GGBS is not that good. What do I mean about workability? Is that it's going to give a more viscous aspect to the concrete, and it's not that easy when you have to pump it. It's also that for pumping is not near the best. So just as an example for the concrete of the big tower that I was talking about, we had to use GGBS just especially to reduce as much as we can the heat of hydration, but also to increase the chloride resistance of the concrete because we were next to the sea. Next one is the fly ash. Fly ash is a byproduct from coal-fired power plants, and the big advantage of the fly ash is that it is something really round, really small, really round. It will help a lot on the workability of the concrete, which means that your concrete will be really flowable and especially really good about pumping. It will be some like small, not bubbles, but round particles that will help for the concrete to go really smoother into the pipes of the pump, for example. In the meantime, fly ash is also really good for the durability, so really good also for the chloride and the sulfates, and it will also reduce the heat of hydration of the concrete. In this case, we are more using the fly ash as 20-25% of replacement of the cementitious material, so a lot lower than the GGBS, but the main impact, I mean, for us, I'm really talking about our experience, is really for increasing the workability. This means that, again, we have also used the fly ash into the concrete of the tower because we had to pump it at really high rise. So in combination of OPC, GGBS, and fly ash, with this, we were able to really produce a concrete that is going to be pumpable, to be resistant to the different attack mechanism, and also reduce the heat of hydration. The last one is the microsilica that we can use in different cases, but the main one is to increase the strength. Microsilica is so small that it will really go inside the small part of the skeleton to close it everything, and also to react with the other parameters, and will be able to increase really well the strength of your concrete. In terms of replacement, we are talking about 5% of the cement replacement that we are using the microsilica. So this helps a lot when you need to reach high strength without putting too much cement. So again, in this case, when you need to go for a high strength cement, you are going to use this, and you can use this in combination with the OPC, the GGBS, and the fly ash to be able to create a concrete that is going to reach really high strength, but also to be pumpable at high rise, and also to reduce the heat of hydration. So this is how we can really choose the cement. And you need really to be careful because the strength of the cement can be really different depending on the supplier that you have. Show you this is to show you a table with the different cement in the European denominations. This is the one that we are using quite a lot in Belgium. So you can see that you have the percentage of clinker, so that's what we call the OPC. And then you have the GGBS, microsilica, and the fly ash, and you can see the different proportion for each type of cement. This is a nice table that shows a few examples, not all of them, but the pros and cons for each cement. And it's really, really helpful to use this kind of table to choose the cement depending on what are the needs that you have. So here you can see that this is the denomination on the first column, and then the constituent to show what are OPC, fly ash, GGBS, silica fume. And you have almost all the pros and cons about the heat generation, the early strength, the end strength, of course, the impact on the workability, the durability, of course. And here you have also a column with the color. Of course, the color is a little bit exaggerated. We don't have a black concrete for when you use a SEM 142.5. It's just to show the difference of color. Why it can be important, the color, actually, it's because on a lot of projects we have, of course, nice architects working on the project, and sometimes they are asking for specific concrete, like, well, everybody knows the white concrete that we are using a lot on big projects, but sometimes it can be also on a usual project. Like a good example is the lock I was talking about in the beginning, where the first concrete was not good at all. There was a requirement of the architect to have concrete that was gray, of course, but it was a specific gray. It was the RAL 1013, I think, something like this. It was really specific. Actually, it's just a light gray. So, but it was really important for the project to reach this color because it was exactly the same color as the cliffs that were just next to the lock. So the good thing is that we have decided for especially for durability purpose, but also it was helping a lot for the color of the concrete to use a cement 3B, which is a combination of OPC and GGBS with more than 65% of GGBS. The good thing is that the GGBS will give a lighter color to the concrete. And because of that, we were able to reach the gray that the architect wants. Well, the fun fact is that I was there at the inauguration of the lock with the boat, and of course it was underwater, and you were already seeing that the concrete was not gray anymore, but green because of the water. So at the end, it was not really a good choice, I think. But indeed, during the execution, the color was there. During the after that, it was not there anymore. When you choose your cement, you need really to be careful also on the weather, especially that you can have, and especially now when you see that in the summer we are reaching the 30, 35 degrees even in Belgium, and during the winter we have minus something. It's important to be able to continue to cast your concrete during the whole year. So you have to choose your cement in consequence. So just want you to show you a table that shows you what kind of cement you can use when it's cold. Actually, the idea behind this is you have to use a cement that is going to react really fast and maybe even produce a little bit of heat to be able to use it when it's cold. That's why we prefer to go for SEM 1, which is only OPC with a strength class fast, and you don't have to put the time to have the concrete going out of the batching plant, doing the slump. So the lower the yield strength, the yield stress, sorry, the more fluid your concrete will be. And the plastic viscosity is really the viscosity of the concrete itself. So is it going to behave like honey or more like water? And you can see that what is the impact of not each material, but some of them, like fly ash, like GGBS. You can see that, for example, GGBS, it will help to have a better workability, but it will give you a more viscous concrete. You can see that the plasticizer will decrease a lot your yield stress, which means that you will have a better slump. When I say better, is to have a more fluid concrete. If you are putting more water, you will decrease everything. You will have something more fluid. So these are the parameters that you can take into account. But why do we need to take into account the plastic viscosity? I will show you an example of two concretes that have the same slump, but different viscosity. For that, well, first, why are we interested in the viscosity of the concrete? Is just, for example, for pumping the concrete. If the concrete is too viscous, you will have more chance to have a blockage into the pipes. So you need to have really a concrete that is less viscous, and that's why you can see that the PFA, the fly ashes, will reduce the viscosity of the concrete. It will increase the workability, reduce the viscosity of the concrete, and that's why fly ash is really interesting in terms of pumping. So for that, which is called the T500. So we do a usual test with the Abraham cone, and you will see on the video that I will show you just after that on you have a ring of 500 millimeter, and you will see how long does it take for the concrete to reach a diameter of 500 millimeter. So I hope that the videos are going to work. So you can see here that the concrete is flowing, and as soon as it is reaching the 500 millimeter diameter, we stop the time. So you can see that it takes 5 seconds for this concrete to as soon as we lift the cone and to reach the 500 millimeter. You can see that the concrete is really nice, really flowable, no segregation at all, but it is still quite a little bit more viscous. You will see on the second video, it takes a little bit more time before they lift. But so you can see that you have the circle with the 500 millimeter, and here it will be less viscous than the first one, and you can see that it will take only 3 seconds to reach it. So you can really see the difference. You might think that it is a little bit too much fluid, but when you see the concrete, you can see that there is no segregation at all. This means that the second concrete is really a concrete that you will prefer to use if you have pumping to do for the concrete. It's a simple test to do, but it can give you really a lot of information. Still no questions? Feel free. Otherwise, we continue. No, it started again. Okay.
Sorry, I have one question.
Yeah, tell me.
How you reduce the viscosity?
Okay, let's go back to the slide here. It's really by using the different type of, no, not the video. It doesn't work. Okay, let me go this way. So if you look at this graph, you can see that the viscosity is horizontal and you can reduce the viscosity by using different type of things. For example, the fly ash will help you a lot by decreasing the viscosity. If you use fly ash instead of GGBS, for example, it will decrease the viscosity. You will have something that is really more fluid, because the fly ash actually is really round, so it will be smoother when inside your concrete. So that's one of the possibility. But you can also work a lot on the different plasticizer that you're going to use. I don't know if you will see this afternoon, but it is really important. You have so many type of plasticizer, super plasticizer, that each of them has a different parameter and different impact on your concrete. So sometimes it's really nice to do some tests and just try different brands even of plasticizer, because it will give you something totally different in terms of workability on the viscosity of the concrete.
Okay.
Does it answer to your
Yes.
question? Yeah.
Yes, thank you.
Anyone else? Now that it's open, let's go back to this then. Just want to give a small word about the carbon footprint. It's quite important in the choice of the material, actually, and especially the cement. Now, especially now in the world, we are looking a lot to the carbon footprint, to the sustainability of everything, and especially the concrete, because we know that concrete is one of the material with the highest carbon footprint. It's important to know what it does, but it's also important to know how we can at least try to do a little thing. And if you take this into account with the huge amount of concrete that we are producing, we know that we can at least try to reduce it a little bit. Just want to show you a quick example. It's a carbon calculator. So it's a calculation of the carbon footprint of 1 cubic meter on one of our projects. I will show you 3 examples. So the first one is we use a SEM1. So remember, it's a OPC only, and the batching plant is on site. Why it is important? It is because this carbon calculator is taking into account everything. It takes into account the materials, so the cement, the gravels, and everything, but it takes also into account all the transportation of each material to go to the batching plant, but also to go to the project site and everything. So that's why it is important to see. So here, batching plant on site, which means that there's not so much transportation of the concrete itself. And actually, it was for the project of the lock where we were reusing all the aggregates, which means that the transportation of the aggregates to the batching plant was not that big. And if we take everything into account, we see that we have a carbon footprint of 299 kgs of CO2 per cubic meter. Okay, let's remember this one. And now that we are taking and we're modifying a few parameters, and here in this case, we are changing the cement. We are using a cement CEM3B, which has a lot of GGBS inside. And we also take into consideration that the batching plant is outside of the project. Here you can see that even if we have the batching plant outside of the project, just by changing the cement, we have now from 299 kg, we are now at 117 kgs of CO2 per cubic meter. Just the choice of the cement has a huge impact on the carbon footprint. And just the last to show you that this still has a small impact. This is the same cement, but with the batching plant on site. And now we are at 105 kgs of CO2 per cubic meter, just by the fact that having the batching plant on site. So you can see that the biggest impact is the choice of the cement. It's really, it has a huge impact. So it's also something that we need to take into account when we want to try to reduce the carbon footprint as much as possible. And especially when you see that this is per cubic meter of concrete. On this project, we had more than 200,000 cubic meter. So if you multiply by this, you can see that we can gain a lot of CO2. So now I try to cover as much as possible about the cement. Of course, there are still a lot of things to say. I think we can talk about the practical aspect during a week. Unfortunately, we have only 2 hours, but in the future, I will say it again, but don't hesitate to contact me if you have any other questions about the cement. Now we are going to have a look at the aggregates. Aggregates, it's important to see that we have different kind of aggregates. We have first the natural aggregates that you can really recognize by the shape of the aggregates. It's more round. You have then the crushed aggregates, usually coming from the quarries, but also from bigger aggregates that you have to crush. These are the two main important ones. What is important to know is here that it will have a huge impact on the workability and also on the strength. Well, but maybe not huge on the strength, but it still has an impact on the strength. The natural aggregates, and this is valid also for the sand that I will show just after that. When you have natural aggregates, so more round, it will have a lot on the workability of the concrete. It's exactly like the fly ash. When it's round, it will give you a smoother concrete that will be really workable. On the other hand, the crushed aggregates, it will give you a higher strength. It can give you a little bit of it will give you a little bit more strength. Sometimes it can be just the few megapascal that you need, but it can be a really a good help. Just quickly, we can also have the light aggregates. This is when you want to do concrete with a low density. And now more and more, and this is still in relation with the carbon footprint, we can use the recuperation aggregate, which is concrete that you crush, and you crush the concrete, and then you can reuse this as new aggregate. At least you can reuse something to reduce the carbon footprint because you're reusing recycling aggregates. It's not easy to use because it has a lot of different parameters, but now more and more we are trying to reuse some concrete aggregates. And now it's the same about the sand, actually. The sand, you have also the natural and the crushed aggregates. In this case, the natural aggregates will have a huge impact on the workability of the concrete. We try to avoid as much as possible to use only crushed sand into concrete, otherwise you might have too much segregation, but also it's really difficult to pump the concrete if you don't have any natural sand inside the concrete. It will have a huge impact. The magic number, actually, that's really practical. I don't think that there is something like this in a book. It's just by seeing it. If you have something around 300 kgs of round sand in your mix design, you will be able to pump it. That's, of course, really general, but just start with that, make some tests, and you will see that if you have to increase it or not. Yeah, so try to remember that as soon as you have natural aggregates, it will have, it can be gravel or sand, it will help a lot in terms of workability, and the crushed aggregates and mostly the gravels will help you a lot on the, well, will help you to give you a little bit more strength. So these are some examples, but I'm not going to go through it too much. And this is what Peter shown this morning. Actually, is you have to combine all these aggregates to have a good curve. Actually, the Excel tool that you have seen this morning, it's also something that we use on site because we need to see what are the local aggregates that are available, and then we put everything together to try to have this curve that is going to be as much continuous as possible to try to have really a good inner skeleton for your concrete. Personally, but again, it's personal, I'm using one of the, well, I'm using two curves that Peter shown this morning. I'm only using this one is the B-line and the Fuller curve. I use these two, and I try to put my curve in between these two. Why? Because I know that the B-line will give me really good really good workable concrete, and the Fuller curve will give me a good strength. If I stay between these two, I know that I will have a really good compromise between a good workability of the concrete and really high strength. But again, it's just by experience that we are doing this. It's I think that everybody needs to have his own choice about how to make the concrete and which rules we can follow. I'd just like to show a small example of when we don't use at all a continuous curve is when we are doing porous concrete. Sometimes on purpose, we are like forgetting a size of aggregate to make like a not a continuous curve, but we make a hole inside, and we are making porous concrete to have the water that is able to go through. I'll just show you a small video when you see that. You see that they are putting the water on the concrete and the water is disappearing directly. And this is something that we are doing for parking spots, for some roads also, when we can do this to avoid to have an accumulation of water on top of the concrete. And for me, it's a really good example of a specific thing about this curve that you don't want to have it continuous at this moment. You need to have a void inside. But that was just a small word. For the aggregates, there's something that is also really important, is the maximum diameter of your aggregate. You need to choose what is going to be the size of the maximum diameter, the size of the biggest aggregate that you're going to have in your concrete. And these are some kind of rules to follow to see which is the Dmax that you're going to use. Of course, if you can, you have to go for the maximum size of aggregate. Why? Because it will give you more strength to the concrete. Well, we can go maybe we can go deeper in this explanation, but try to remember that try to go for the maximum that you can in terms of the maximum diameter of the concrete. And then you have to follow a few rules to avoid that you will have big aggregates that are going to be stuck in between two rebar, or if you have two big aggregates in a pipe of a pump, it will be stuck, and then again you will have a blockage, and you will have the pressure will go too high. So you have really to go for the maximum one, but by following some rules. And sometimes that's why also we are making some what we call micro concrete with really small diameter of aggregates, is just because of this or because of pumping and things like this. And just want to show you some examples where sometimes it's quite difficult to even make to put some aggregates in your concrete, because when you see the reinforcement, you really think, okay, well, where can I put a little bit of concrete? And these are two pictures that I took from Besix project, so it's not something that you Google on internet and you can find some jokes. This can really happen on site. The first one, it was the one on the left. It was a column, so we had to deal with it. The second one, it's still unbelievable that they have done this, but at the end they have removed it and they did they redid the whole design. It was supposed to be a crane foundations, so at least it was not a structural element. So at the end, for the aggregates, what is important to remember is that you need to have a continuous cumulative curve of the sand gravel combination. I think that you have seen this morning quite a lot now. For pumpable concrete, you need more fine to have a continuous curve also, and round sand. Remember, 300 kgs of round sand per cubic meter, it will help you a lot on the pumping of the concrete. Something that I didn't talk about, but it is quite important actually, it's also the nature of the aggregates, because we are using limestone aggregate, porphyre sometimes, granite, a lot of different nature of aggregates. And actually it's important because, for example, the limestone has a lower Young modulus and a lower thermal linear expansion coefficient. And why this is important is that, especially for the expansion coefficient, when you have massive concrete, if you have limestone aggregate, as the expansion coefficient is lower, you will have less movement of your concrete when it's heating up because of the cement hydration. When there is heat going out of the cement during the hydration, the concrete can go up to 85 degrees, which is really high when it starts at 20 or 30 degrees. So it will heat a lot. If you have limestone aggregate, it will expand less, and you will have less problems of difference of temperature inside your element, which means that you will have less problems of thermal cracks, because you can have, if you have a difference of temperature inside your element, you will have the center of your element that is going to expand, and the top of the surface of the concrete will expand a little bit less, and then you will have cracks appearing. If you have limestone aggregates, you can accept to have a differential of 35 degrees between the center and the surface of the element. Where when you have siliceous aggregates and other type of aggregates, you are limited to 20 degrees. So when you have really big elements and when you have massive concrete, it's really important to know what kind of aggregates do I have in my concrete? Or do I have the opportunity to choose my aggregate? Do I have the choice between limestone aggregates and something else? So this is why it is important also. On the other side, when you need to have a Young modulus that is quite high, you will go for other type of aggregates. This is typically when you have cantilevers, for example, or when you have big buildings where the Young modulus is quite important because of the deformation. You have also maybe the opportunity to choose your aggregate to increase the Young modulus. We had the case in one project where we were able to reduce a lot the sections of the columns just because we went to choose a specific aggregates to increase the Young modulus and then to have less deformation. So you can see that this is the opposite for the siliceous aggregate, so higher Young modulus and thermal expansion coefficient. So as I said, the crushed aggregates provide higher strength, and the higher the Gmax, less cement is required for the same strength. So the higher Gmax, you will have more strength. It's just something that you need to be careful with on site. It's also this is something that you cannot really see directly on paper, but you have to really be careful with the contaminated aggregates, because sometimes you can always, and this is also in relation with you have to deal with what you have locally available, because sometimes you might have really aggregates with a lot of dirty aggregates. Actually, here in this case, we had the case where we had a lot of mud inside. And we had a lot of troubles with the workability just because there was a lot of it was totally contaminated. I will not go too deep because I see that the time is running. As I said, here it's when I say a quiz, it's just there are 3 questions, and let's see if we can try to answer this together. So, just a few examples. If you want to make a concrete block of 1.5 by 2.5 by 10 meters, so these are blocks for quay walls usually. So you see it's really big blocks, really massive concrete element. What kind of cement are we going to use, and which Dmax are we going to use? Does anyone want to try?
Hey, can I answer?
Yeah, sure.
For the type of concrete, I think mixing of fly ash and GGBS can be good, because we can reduce the viscosity as you mentioned, and
yeah.
On the other hand, we can have we can use fly ash to reduce the bad workability of GGBS, and on the other hand, we can improve the durability of the specimens on one side. I think.
Yeah, that's really good actually. In this case, so the durability here, I didn't mention it, but these blocks are non-reinforced. But we still need to be careful with the attack of the sulfates, because this is on the concrete itself. So it is correct, but in this case, the fly ash can be. It's not absolutely necessary to use it, because it's a block, but it's not something that we have to pump at high rise or on a long distance. So at this moment, the GGBS will not be a big issue in terms of workability. But your point is totally correct. If we need to pump maybe a little bit further, if we need to pump to have these blocks done from a few hundred meters, then it might be necessary. But in this case, it's something that you can cast directly. So indeed.
For instance, in this point, if the highest strength is considered, we can use instead of that the microsilica instead of.
Yes, exactly.
Yeah.
Indeed. Usually this type of blocks, the strength is not absolutely important, but indeed, if it is the case, we are going to use microsilica. Correct. In this case, there is something that you didn't mention that is really important. Does anyone has an idea about that? Another parameter that we need to take into account by keeping in mind that we have something really massive.
Yeah, I think the problem is the heating of the concrete, because it's
Exactly.
a concrete mass.
Yeah. Exactly. It's really something that is massive. If we take just OPC, it's going to heat a lot. So indeed, we are going to use GGBS and or fly ash also to decrease the to increase the durability, but also to decrease the heat of hydration. If you don't do anything in this kind of, if you're just using a regular concrete, you might reach easily 70 degrees inside the concrete. So which is really too high. So indeed, at the end, we need to have OPC, because it's absolutely necessary to use OPC, otherwise the reaction will not occur. And we use GGBS and or fly ash to reduce the heat, to increase the durability, and these are the main things. And what about the maximum diameter of the aggregates that we are going to use? As I said, it is not reinforced. I don't need a value, but just an idea. Are we going to go for the smallest one, or are we going to go for the biggest one?
I think for the biggest one is better.
Exactly.
Yeah.
As soon as you can, go for the biggest size of aggregate you can. You will decrease a lot the cement content of the concrete for the same strength, which is very good in terms of heat production, in terms of carbon footprint also. And well, we are talking about practice, so in terms of money also, cement is one of the most expensive thing in the concrete. Okay, excellent. In this case, I am going to use what would be the preferred type of aggregate, limestone or granite? I didn't hear. I think. Yeah. Why?
Granite, because I think the young modulus.
Actually, no. It's a block. The young modulus is not really important in this case. It's the block is just by gravity, so young modulus it's not really big deal. But so actually it's not granite, it's limestone. And why is it better? Because the limestone will have a lower expansion coefficient, and as it is a massive structure, it will expand less just because of the heat, because you have limestone. So you will have less problems of thermal cracks. Of course, it's better for the self-healing to occur, to test, to have cracks, but usually we try to avoid this. Okay, now we want to pump concrete for a high-rise building. What should we put into the mix?
I think one of the most important is, for instance, we can use super plasticizer.
Exactly.
GGBS. I don't know. No, GGBS is not good for workability, but fly ash should be there.
Excellent. If you have only this information, just to know that you have to pump for high rise and you don't have any information about what is the size of the elements, what is the strength and everything, indeed, we are going to use fly ash It's almost this is the best for this. Super plasticizer also to have something that is really fluid to be able to pump the concrete. And there's still something that might help.
Still.
The type of aggregates.
Yeah, exactly.
What
kind of aggregates?
River aggregates, natural aggregates.
Yeah, natural one, round one. That's the best to pump. Just to show you an example, this is a pumping trial that we have done. This is altogether, it's 1 kilometer horizontal, and this it's quite interesting because it has been done together with Putzmeister. I don't know if you know the company. It's a pumping company from Germany. It was done together with them to be able to calculate based on the result that we have there on 1 kilometer, taking into account the size of the pipes, the corners and everything, to calculate what will be the pressure in the pipes when we do it vertically. So it's a test that you do for high-rise building. When you cannot do it as a real test, you can calculate like this. And this has been done again for the tower to see if it was possible to pump the concrete at more than 800 meters in one go. Another one, sewage treatment plant. Do you remember what kind of attack mechanism you are involved? What can occur on the concrete in this kind of project?
Yeah, I think chloride attack and carbonation.
Yeah.
Are some of the most important, especially for reinforced concrete structure.
Exactly. Exactly. You can have also sulfates from the water that is inside.
I think. But chloride, I think, and carbonation are more important.
It depends actually on when you have a project of sewage treatment plant, you really need to work together with the designer, such as Veolia or people like this, the client actually. They need to give you the content of the water that is of the process. They need to give you all the information about the process or the process of the plant to see exactly, okay, in this type of tanks, I will have a lot of chloride. What is the sulfate content of the water that is coming in also, because this might be very high at the beginning of the process. So this is something that you need to take into account for the chlorides and the sulfates. The carbonation, of course, it will happen all the time because you have water, you have the CO2 that is present in the air, so you have to take this into consideration. And then, depending on the country, freezing also.
Mm-hmm. Yes.
Do you remember what kind of cement is the best usually for that kind of attacks?
I don't, I'm not certain, but I think cement type 3 may be good.
Yeah, that's a really good choice. Indeed, cement 3 is a combination of OPC and GGBS, and GGBS, such as fly ash, is really good for the durability. So in terms of resistance to the chlorides, the sulfates is really good. Just for information, in terms of carbonation, CEM1 is better. Just for information. But usually,
cement type 1 is better than 3, you mean?
Yeah, for carbonation only.
Mm-hmm. Just carbonation.
Yeah, usually, well, CEM1 is better for in terms of durability is only for carbonation, but the CEM1 is better for to go faster, to cast concrete in during the winter and things like this.
Mm-hmm. Okay, thank you.
But it's bad for carbon footprint also. Okay, you saw it was not so many questions, but if you have questions now, don't hesitate.
I have one question
about
aggregates. Regarding to the sea sand, is there any treatment for chlorides that should be done?
Very good question.
To put into the concrete.
That's a very good question. Yes, well, there are some differences. You can use the sea sand just like this, depending on what is what is the necessity of the concrete. If you don't have any reinforcement, usually you don't really need to do anything, because the chlorides are mostly attacking the rebar. Of course, in the standard there is still a limitation, but anyway. As soon as you are using reinforced concrete, and even worse if you are using post-tensioning concrete, then it's really important to verify the chloride content of your concrete. If you have sea sand, you will have chlorides inside your sand for sure. So you have to test it to see what is the quantity of chloride into the sand. It is important to test it because sometimes, and I already had the case, we have tested the sea sand, and it is there's almost nothing of chlorides inside the sea sand. And this is depending on how they are doing it, because if they take the sea sand and they keep it in storage outside during a long period, just by the rain, it will be washed. It will be washed from the chlorides. But otherwise, you can always wash the sand. So it's going through a whole mechanism with a lot of water, and to remove the chlorides from the sea sand. So totally correct.
Thank you.
And what you have also to be careful with is the shells that you can find into the sand, because it's not that good also for the strength. Any other question?
I have another question.
Tell me.
I saw that Khalifa Tower in Dubai, and some years ago, and I have one question about that. The basement of that place is sandy, yes?
Yeah.
And what do you do to, for instance, not having problem with the basement, like settlement and something like that?
Oh, that's a really good question, and to be honest, to go deeper in the answer, someone else would need to answer, because it's more something on the design point of view. But what they did is that the piles that they have done. So it's something that you have to calculate. It's they needed to go really deep into the ground to go below the sandy part, and to find the rock, to be really into the rock.
Mm-hmm.
But I don't know that much about that, because it's something totally out of my scope.
Okay, and I know that this is very high, this tower, and there is different temperature in each level. Yes. What do you do for that? Do you have a different mix design in different level or not? You think something?
It's a really good question. Actually, we consider usually that we lose 1 degree per 100 meters of altitude. So we know that we will have 8 degrees less at 800 meters. This can be neglectable, but actually it will help us, because the concrete is already quite hot when we do it, because in Dubai the temperatures are really high. So it will help us a little bit to slow down the reaction. And for us it helps a lot, because first the concrete starts at 32 degrees at the beginning. I will just show you now how we do that. And the concrete temperature is going up during the pumping, because of the friction of the concrete into the pipes. The temperature will go higher. So actually, it's a little bit better for us that at the top of the tower it is a little bit cooler than at the bottom. But I take the advantage of this question to go on something else. Again in Dubai, because it was a really good example. We did recently the canal in Dubai, and for the Dubai canal, it was big blocks, pretty much the same as the one I was talking about, the first question. Big blocks that were putting together to do like Lego, that we put together to do a quay wall. These blocks are quite massive, And we did two different mix design, one for the summer, one for the winter, because we knew that during the winter, when it's 15, 20 degrees outside, we were able to use a cement that was going fast. So we were using a CEM1 with a sulfate resisting CEM1. We were using this one because we needed to go fast, and we knew that because it was cold, quite cold outside, we won't have any problem of temperature in these blocks. On the other hand, during the summer, when it is 50 degrees outside, we were using a mix with a lot of GGBS because we knew that the concrete was going to be really hot and it was going to go too high in temperature. So it's really winter and summer mix design. And actually, we can do this also in Belgium, for example, because we know that we will need a cement that is going to react really fast during the winter, and we can go for something a little bit more usual during the summer.
Okay, thank you.
Any other question?
Yeah, I have a quick question.
Tell me.
So when we discussed the question on the type of cement that we will use in sewage treatments, and you mentioned that if it was a carbonation attack that's going to happen, we will use CEM1 and not CEM3 because we need to avoid using GGBS. My question is, what would we do when you have multiple damages at the same location? What type of cement and how do you choose that? It's very often that we have more than one durability parameter that's attacking.
Exactly.
So what do you do then?
Exactly. It's also like in the example with the drawing with all the exposure class, you can see that at some location you will have freezing, chlorides, sulfates, carbonation, well, everything on the same concrete. So good question. How can we deal with this? Again, I will tell you on a practical way. Let's go straight forward. I will go for a CEM3B. This is my point of view. Why? Because it will be really good in terms of almost everything except the carbonation. And the carbonation will not be that high compared to the other problems that you can have. And the carbonation, you can also work on it by increasing the cover of the concrete on the rebar. You can also put some painting or protection on the concrete to avoid the CO2 to penetrate too fast. And then the best solution is self-healing concrete, of course, because actually the cracks are the worst for the corrosion of the rebar. So I'm sure that in a few years we will use only self-healing concrete, so there won't be any problems then. I hope this answers your question.
Yes, definitely. Yes. I did want to know what they do practically, so it was a good answer. Thank you.
Sometimes also just want to point this. Sometimes we put paint, epoxy painting on the rebar to protect directly the rebar. This is something that we try to avoid because you can have a lot of problems with that. You lose the bonding of between the concrete and the rebar. As soon as during the manutention of the rebar, you always have a little bit of painting going out. So something that we try to avoid as much as we can. But at least you know that it exists.
Yeah, thank you.
You're welcome. Any other question?
If I may ask a question, you've been mainly focusing on durability, but in high-rise buildings, I think you can also have problems with long-term deformations. Yes. Because you have so much concrete stacked on top of each other. So if it starts creeping and you're not entirely certain what the value of the creep deformation will be, you could also get some problems, I think. Is this something you also take into account with the mix design?
To be honest, we don't take into account the mix design when we are doing it, and I'm not saying that it's not that it is the right thing to do. I'm really talking about what we are doing on site. But as soon as it is important, as soon as we have the mix design, we are doing creep tests to know exactly, and then we are working together with the design office to see what can be the impact.
Okay.
But yeah. To be honest, we don't work that much on this on the mix design.
Okay,
I cannot say if it is the right thing to do or not, but this is how we do.
Thank you.
Welcome. Any other question? I think I will go fast on the last slides because it is a little bit related to the mixed design, not that much, but well, you will see, and maybe we can discuss it further. Just want to talk about the maturity. Maturity, it's something that is important that we start using a lot. It has an impact on the mixed design because it can help to reduce the cement quantity. Sometimes we are putting too much cement just to have an early strength, really early, to be able to remove the formwork as soon as possible. It's not good for the price. It's not good for the shrinkage. It's not good for the heat. It's not good for a lot of things. So that's why we use sometimes the maturity. What is the maturity of the concrete? Is just the fact that you can link 3 parameters of the concrete together: the temperature, the compressive strength, and the age of the concrete. As soon as you know 2 of them, you can calculate the third one. In our case, what is the most interesting thing for us is, the most important thing for us is the compressive strength, and what is easy to collect is the age, really easy, and the temperature. Temperature, you just need to put some thermocouples inside the concrete. It will measure automatically the temperature of the concrete, and just based on the temperature and the age, you can calculate the compressive strength, the real one. For that, you need to first do some tests, to do a calibration curve. It will link, so you can see the MPa, you have the concrete strength, and here in degree hour, you will have the age and the temperature. So this means that if you measure the maturity in the concrete, you can calculate the real-time strength in the concrete without destructive testing, and this can help also. Also, you take into account the temperature that is inside your concrete, which is absolutely not the same as the temperature inside small samples that you take into the lab, and then you can crush. And this means that you take into account the temperature of the element and the temperature going out of the hydration process, which is going to accelerate the compressive strength. And this means that you will be able to remove the formwork or do the post-tensioning faster than foreseen. This is an example of Concremote, which is a product coming from BAS. BAS is now known as Concrefy, that you will see tomorrow. There are other material. There is also Maturix that we use a lot. But anyway, this is just to show you the example. You will have in real time the strength of the concrete. I will show you a better example. This is the lock that I was talking about a few times, with the color of the concrete, with the bad concrete at the beginning with the segregation. And we use this system on this lock. We had walls of 1 meter thick, 10 meter high, that you can see here, and we wanted to, and this was on really a long distance. So it was really interesting for us to remove the formwork as soon as possible. So what we did, we measured the temperature inside the concrete, so you can see the different curves. You have 3 curves where we measure the temperature in the center of the wall and on the sides, and then you have also the outside temperature. Just based on the temperature that we are measuring, automatically we had in real time the compressive strength of the concrete that was calculated. And you can see that we needed to have 5 megapascal to remove the formwork. As soon as we were reaching the 5 MPa on each location, we knew that we were able to remove the formwork without any problem. Based on this, we were able to remove the formwork after 2 days instead of 3. So for each walls, we won 1 day. In terms of planning, this was amazing for us. I can go really deeper in this. Unfortunately, we don't have enough time, but if anyone is interested, we can maybe discuss this on another day. The last thing I wanted to talk about is, again, the mass concrete. Why? Is because it's something that for us, it's really important, because as I said, as soon as you have a thickness more than 1 meter, it has a huge impact on the thermal problems that you can have, especially the thermal cracks and the DEF, so the delayed entragite formation. We are using this a lot in the Middle East, and you know that it's really hot in this country, so that's why we have a lot of troubles in there. Just to show you an idea of the temperature of a mixed design, if you have the cement at 40 degrees, the aggregates at 45, and the water at 30, and this is really usual values for that, you have a concrete at 41 degrees. It's too high. The setting time will be too fast. It will produce too much heat because it starts at 41 instead of 20. So you will have a lot of troubles. And I wanted to talk about that also because it's not really working on the mixed design. First, you need to work on the mixed design by choosing the right cement, the right composition, but it's also working on the fresh concrete. It's not the mixed design, but it's almost the same because it is at the moment when you put all the materials together. How to reduce the temperature of the fresh concrete? I will ask you first, does anyone have an idea? How can we deal with the concrete, with the different materials that we were talking about, so the cement, the gravels and everything, the water, how can we do to reduce the temperature of this concrete? Does anyone have an idea?
Reduce the temperature of the water and the aggregates?
Exactly.
Maybe?
And how can we do this? Well, water is quite easy. You just put the water through a pipe in a chiller, and you can have a water at 2-3 degrees instead of 30 degrees. This will have already a huge impact. As you know, we have between 150 and 200 liters of water. It's still a considerable amount. So if at least you can gain some degrees on this, it helps a lot. But how can you reduce the temperature of the aggregates? Do you have any idea? No? So, okay, as we don't have so much time, I will go through everything now. First, aggregate in the shade. Imagine you have the aggregates in the middle of the sun. You can just put a roof on top of it in your stock. You will gain at least a few degrees. I'm also talking about that because this can help also even in Belgium. When it's really hot during the summer, you can have troubles with the temperature and then the setting time of a concrete. If you follow a few of these rules, not all of them because you will not be able to follow all of them, but you can really gain some time and maybe not using a retarder in your concrete because it costs a lot of money also to put some retarder when it's really hot outside. So aggregates in the shade is one first thing. As we said, chilled water, sprayed aggregates. Sprayed aggregates, sometimes we just put some sprayed water on top of the aggregate. It's like when you're taking a thing like this with water that you spray in your face, it feels fresh. It's the same idea. It's just because the water is evaporating, it will reduce a little bit the temperature. Ice flakes. In the Middle East, we are using quite a lot. We are putting ice flakes into the concrete. What we do is we replace a part of the water by ice flakes. The ice flakes, something like this. So it's really crushed ice. For those who are not really able to imagine, it's exactly the same that you put in your mojito. Usually the people are really seeing what kind of ice it is. And the idea is that it will melt. And by melting, by going through from solid to liquid, it will need energy for that, and it will take the energy from the surrounding, so from the concrete. It will reduce a lot the temperature of the fresh concrete. And then the last solution, you can also put liquid nitrogen. So this can be done also, but it is very, very expensive and also very dangerous because when you put it, usually you have to do it manually, and this can be very dangerous. Just to show you some example of what we can do. So you can see here it's a block like pretty much the same as we were talking about during the exercise. Huge block producing a lot of heat, and we have some possibilities in 2 dimensions. First, to see what is going to be the highest temperature inside the concrete. So here you can see that we are reaching 65 degrees inside the big block. We have We have other software where we can do this in 2 dimensions. Really interesting also for raft and things like this. And case study, I think we don't really have the. I will go really through it just to show you that's, yeah, it was for the raft of the Royal Atlantis hotel in Dubai. It was quite a big raft, and so it was very hot outside, 3 meters thick, pouring mid-July, so when it was really hot. We were limited to 70 degrees, and the concrete, and that's why I wanted to show that, is that we are talking about the mixed design, but the thing is that often on site, the mixed design is coming directly from the batching plant, and if they are not really going in deep in the choice of the mixed design, you have to find mitigation measure afterwards. In this case, it was the case because they asked me to check the temperature, but the mixed design was already fixed. We were not able to work on this. It was something that it was, okay, no, you cannot touch the mixed design. It is like this, and we are casting tomorrow. So you don't have really the choice. And in this case, it would have been better to increase the GGBS, for example, because it was something that was really thick, and we don't need to have a concrete that goes fast. So what we did a simulation, and because of that, it was necessary to put 90 kgs of ice per cubic meter, which is a really huge amount. It would have been better to work on the concrete mix design before. Another solution to avoid problems of temperature, and again to show that first you have to work on the mix design, you can use cooling pipes. So it's pipes with cold liquid embedded in fresh concrete. Another example, it was a big beam in Cameroon. It was absolutely necessary to use the same one, which is absolutely the worst cement to use for big elements like this, but it was necessary, absolutely, we didn't have the choice. So we have put, so in the first calculation, we were seeing that we were going really too high, it was 75 degrees. And the first calculations with the cooling pipes were showing that we were already going down at 67 degrees. And we still have a red part where we had to put another pipe inside to reduce. So it's really pipes that are into the concrete, and you have cold water going inside to cool down the concrete during the hydration process. And it looks like something like this. You have the pipes that are going inside the concrete, but it costs a lot. Logistically, it's a nightmare, and you always have troubles with the machines. Let's go to the conclusion, because I still want to have 15 minutes if possible for questions if there are. But as a conclusion, the first thing to check is what are the needs of the concrete, what are the needs of the project where you are. You need to see what is going to be the durability of this concrete. Am I going to pump it? Do I need a flowable concrete? What kind of element? Is it going to be a massive element or whatever? So all these parameters, you need to take this into account when you choose your material. And this is why it is important to meet the different supplier locally. You will not be able to find the best cement or the best gravels that you want everywhere in the world. You have to deal with what is around your project. And then you have to deal with it, and you have to do the best concrete you can with that. So choice of material depending on the availabilities and the needs, as I said, and then like I just show you the additional principle just to show you that it's important to work on the mix design. This is the first thing that you need to do on site. Work on the mix design, and then if you don't have the choice because of the availabilities, then you can go for other principles like putting ice inside, or putting pipes, or using microsilica to import microsilica from somewhere else. But first, try to deal on your mix design with the resources you have. Thank you very much. And like this, I think we still have 15 minutes if you have other questions, or to have a bigger lunch break.
I have some questions.
Tell me.
For instance, if you have use ice flake, do you have a different water to cement ratio or not?
No, because you need to replace the water by the ice flakes. So example, if in your calculation you know that you need to reduce your the temperature of your fresh concrete, you need to use 50 kgs of ice, then you will remove 50 liters of water from your mix design, because you know that this water will become the water, because you know that the ice flakes will become water in your mix design.
Okay, and another one is that you work on the mix design based on that you have a sustainable structure. But if, for instance, I don't know, you monitor the durability properties of your structure or not, and if you have any problems like chloride attack and corrosion of reinforcement, what do you do?
You mean if during the lifetime of the structure you have troubles? Yeah. Then it's another training that you can give on repair. Then it's something you can talk about during hours also. But indeed, when you have something that you need to repair, you need first to understand what is the cause, first to avoid that it's going to occur. If you remember the one of the first example I shown in Mozambique, it was absolutely necessary to understand what was the cause of this corrosion, and it was coming from the inside because of the seawater that they used in the mix design. If we didn't have a look at this, we would have repaired everything, and then the corrosion would have continued from the inside. So first, you need to understand what is the cause, and then you can repair by a lot of different methods depending on how big is the problem, where is the location, and then you can always repair. But then it's really another discussion. There's a lot of different possibilities.
And the last one, I think, you show the Palm Jumeirah and the hotel that you are working on that.
Yep.
I know that Jumeirah has another mechanism, and as I know correctly, I think it has a sandy basement.
Yep.
Under that, and under the sandy basement there is water. Yes.
I think so, but again, it's going to be the same type of question as the Burj Khalifa.
The mechanism in Dubai is stranger for me. Some companies have different designs.
Methods, yeah. Well, again, as the Burj Khalifa and the Atlantis, we didn't do the design. It was from a design office totally separately. So in our case, we just build in kind of the building. To be honest, for the Atlantis, I think they are also working with piles, but I really don't know how did they do for that. Unfortunately, this is really more a structural designer to answer. Unfortunately, I don't know. Yeah, unfortunately, I cannot answer that. I'm really sorry.
Okay, no worries. Thank you.
Welcome.
Are there other questions? Or all ready for lunch?
I have more a small one regarding an example that you mentioned in the beginning of the presentation.
Yeah.
That you discovered that the seawater was used in one of the structures. It would be by titration analysis, analyzing the total chlorides, or what is the test method to use to discover this?
Good question. You have to see what is that's going to be difficult to explain like this without being in real. But when you do the chloride the chloride analysis, you have to do it by slices of concrete to see if the chlorides are coming from the outside. How can I explain that? You really see if the chlorides are inside the element or coming from the outside. This is in short. I don't know if you understand the idea. Yeah? Well, that's something like this.
Thank you.
Okay, I think it's now exactly 1 o'clock, so you did a perfect timing. Very good. So I would like to thank you a lot because it was really interesting with very nice applications of buildings and where you have to make choices for the right concrete for that application. That's really interesting to see and to see all that process. And also I was very happy to see in the end that you applied this tool heat to look at the massive concrete because once I developed that in my previous life. So
Oh, really?
it's nice to see these pictures back. Yeah.
It was not it, and it was not especially for you, but I'm happy to have used it. We used it a lot. We used it.
Yeah. No, yeah. Okay. That's nice. Nice to see. Yeah. Okay. Then thank you again. And
Thank you very much.
well, I think then we go for lunch break now, and we will be back at 2 o'clock sharp. Okay.
Enjoy the rest of the training. See you.
Thanks. See you.
Thank you.
Thank you.